Going through example 4.4 from the book. It's a sort of continuous beam. It's actually one beam, but because we have some external forces at the middle of this beam, we have to define a node like node number 2. So it's a combination of two beams connected together at node 2. So we have three nodes and two elements. And as you see in example 4.4, and there are the values for modular elasticity and second moment of inertia, as you see. And I just put it uh, here just to read the values. You can have it with yourself as well to follow up with the ETABS process. For this example, I use matrix SI because I'm going to work with kilonewton and meter. I will go with grids only, and I need really 3 grids, and the spacing everywhere is 3 meters. So one story is enough, 3 meter, 3 meter. This is enough for me to start with modeling this beam. It's up to you to define which plane are you gonna use. I go with plane number 1. So I'm working in XZ plane. I start with creating my beam elements like this. So as you see, I have 3 nodes and 2 elements, and I need to define the elements properties. So first of all, I define my material or modify an existing one. This is my material, and I set it to 0 because I don't want any extra load to be applied to the problem. The module of elasticity is 210,000 megapascal. 210 gigapascal means 210,000 megapascal. So this is my material. Section property, in terms of frame section, I will add a new property from the general type, and I name it my beam. So the material is my material, and here we are for the second moment of inertia in terms of centimeter. For it would be 40,000. 40,000 is it is. So press OK. Then I grab these elements and assign frame section properties like my beam, and now my beams have the specific material and section. So for the support definitions, I get these two and assign them to restraints, and they are fixed supports. In the middle, we have some external loads, like we assign joint loads as a force. And as you see, we have 10 kilonewton along Z, minus 10 kilonewton because it's upside down. And we have an external bending moment counterclockwise, if you see example 4.4. And in ETABS, if you take a look at in the right-hand side window here, see X, Z, Y. So we are working in the XZ plane, and the example 4.4 says there is a counterclockwise external bending moment equal to 20 kilonewton meter, which means that it is not in line with this green y-axis. It's against it. So it's minus 20 kilonewton meter for moment global YY. So press OK. And now I think we are ready to go. I just name it example 4.4. Before I'm waiting for the ETABS to finish, but before that I can peek on the solutions. I want to compare these two values, d2y and phi2. d2y is the vertical deformation at the middle of the beam, and phi2 is the rotation at the middle of the beam. So let's see what we get from ETABS. And if I go to show the deformations, the deformation is not symmetric because you have that external moment which rotates the beam. And here we are. If you take a look at what we got here, UZ is minus 0.135 in terms of millimeter, which is, yeah, fairly close to the manual calculation. And the RY, which is the rotation along the y-axis, is 0.409. And yeah, that's very close to the manual calculation. So this is the solution for example 4.4, just more elaborate with the model just to see the internal moment distribution or the other parameters as the structure analysis output. Thank you for watching, and